A transformer is one of the most efficient and versatile pieces of equipment used on T&D systems. In order to function properly, a transformer has to be connected properly. In this program, we're going to concentrate on single-phase transformers and the basic principles that apply to transformer connections. We'll look at some examples of how transformers can be connected to distribution systems to provide single-phase service. We'll also show you examples of how single-phase transformers can be connected together to provide three-phase power. Let's start by reviewing some basic information about transformers and how they work, and identifying some standard features found on single-phase distribution transformers. A transformer is an electrical device that changes the values of voltage and current. Inside a typical transformer are two windings, a primary winding and the secondary winding. Both windings are wrapped around a common metal core, and there are no physical connections between the windings. The primary winding of a transformer is rated and insulated for a specific primary voltage. Voltage is applied to the primary winding by connections to a primary distribution system. One or more insulated primary bushings mounted on the transformer housing provide the connection points between the ends of the winding and the primary system. The secondary winding of the transformers is rated and insulated for a specific secondary voltage. When energized, the secondary winding supplies voltage to a secondary load. Connections between the winding and the load are made through insulated secondary bushings. Now, even though it functions as a single unit, the secondary winding in a single-phase transformer is actually made up of two individual coils of equal size that are electrically connected together. How the two coils are connected can vary to how the transformer is used. We'll look at these various connections in more detail later on. When a source voltage is applied to the primary winding, the resulting current flow creates a magnetic field. The magnetic field cuts across the secondary winding, inducing a voltage. The ratio between the number of turns in the primary winding and the number of turns in the secondary winding determines the value of the secondary voltage that a transformer can supply to a load. Now, let's take a look at some examples of single-phase transformers that are commonly found on distribution systems. This is a single-phase, single-bushing transformer. It provides single-phase voltage, typically rated at 120/240 volts to a secondary load. On a single bushing transformer, the primary bushing is generally mounted on the top of the transformer housing. The bushing is insulated for a specific primary voltage and serves as a connection point between one end of the primary winding and an energized phase. In this example, a surge arrestor is also mounted on the housing to protect the transformer from damage caused by voltage surges. The other end of the primary winding is connected to a case ground located on the side of the transformer housing. The case ground is used to connect the transformer to a grounded system neutral. Secondary bushings are also located on the side of the transformer housing. The bushings are insulated for secondary voltage and serve as connection points between the secondary winding and the secondary load. Another common transformer design is the single-phase, two-bushing transformer. This unit is also typically rated to provide 120/240 volts to a secondary load. The primary bushings are insulated for rating primary voltage and serve as connection points between the primary distribution system and each end of the primary winding. As with the single bushing design, secondary bushings are located on the side of the housing. A third type of transformer is a dual voltage transformer. Dual voltage transformers are similar to the other units that we've discussed, except that on the side of the housing is a two-position switch. The switch can change the number of turns in the primary winding. A dual voltage switch allows the flexibility of energizing the unit using two different primary voltages. One of these features is the designation of the primary bushings. Primary bushings are located either on the top or the sides of the transformer housing. They are designated by the letter H and a number. By industry agreement, when viewed from the secondary side of the transformer, the bushing mounted on the left side of the housing is designated as the H1 unit. This designation remains the same for all pole-mounted transformers. On two-bushing transformers, the bushing on the right is designated as the H2 bushing. Secondary bushings are designated by the letter X and a number. Each bushing is connected to one or more ends of the secondary winding. As we indicated earlier, a secondary winding is actually composed of two separate coils connected together. Depending on how the coils are connected, there may be 2, 3, or 4 secondary bushings. The polarity of this transformer is additive. The 3 secondary bushings in this example are designated as X3, X2, and X1 when read from left to right. If the polarity of this unit were subtractive, then the bushings would be designated X1, X2, and X3 when read from left to right. Another standard feature on a single-phase transformer is the nameplate. A great deal of information is stamped on a transformer nameplate. For our purposes, the information we're concerned with is the unit's polarity, kVA rating, voltage rating, and percent impedance. Let's look at what this means in terms of transformer connections. The size or capacity of a transformer is designated by the term kVA, which means kilovolt amperes. kVA is an indication of a maximum load that a transformer can efficiently handle. This unit is rated at 50 kVA. The voltage rating of a unit is also indicated on its nameplate. In this example, the primary voltage rating consists of two numbers separated by a diagonal line. The rating is 7620/13200Y. The first number, 7620, indicates that the primary winding is rated and insulated for 7620 volts. The second number, 13200Y, indicates that this unit is designated for use on a 13.2 kVY primary system. In this example, the secondary voltage that can be supplied to a load is also indicated by the two numbers separated by a diagonal line. In this case, 120/240 indicates that when the unit is properly energized, it can supply a secondary load with both 120 volts and 240 volts. The last thing we'll discuss on the nameplate is the term percent impedance. Impedance is defined as an opposition to the flow of electricity. Typically, percent impedance is represented as 1 to 5% depending on the capacity of an individual unit. In this example, the percent impedance is 1.7%. When connecting units together to form a bank, it is very important that the voltage ratings of the unit are identical and compatible with the primary system. In this part of the program, we've reviewed some basic information about transformers. Take some time to review this material in your text and answer the questions. When we come back, we'll look at two types of primary distribution systems. A substation transformer supplies power to a distribution system. The weight of the windings on the secondary side of the substation transformer are connected together determines if the primary system is a three-phase delta system or a three-phase Y system. We'll look at each of these systems beginning with delta. Here we have simplified illustration of three identical transformer windings. In a delta system, the ends of each winding are connected to the ends of the other two windings. When shown graphically, the windings form a triangular shape that resembles the Greek letter delta. In a three-phase delta system, each phase originates in a point where the ends of the two separate windings connect. These points are 120 degrees apart and typically designed A, B, and C. Between points represents the phase-to-phase voltage of the delta primary system. In a Y system, the windings are connected differently. One end of each winding is connected together at a common point which is called the system neutral. In most cases, the system neutral is grounded. The other ends of the windings are positioned 120 degrees apart from each other. When shown graphically, the connection resembled the letter Y. Traditionally, the ends of the windings are labeled A, B, and C. The system neutral is labeled N. Each phase of the three-phase Y primary system is formed by a connection between the end of a winding and a neutral. In this example, connections between A and neutral, B and neutral, and C and neutral each represent a different phase of the three-phase system. The voltage value of each of the phases is the phase to neutral voltage of the primary system. The graphic representations of delta and Y systems are referred to as phasor diagrams. Phasor diagrams can be used to show a number of different relationships within a power system. For our purposes, we'll use phasor diagrams to demonstrate primary distribution systems and how transformers can be connected within those systems. We'll begin with the delta system. The delta primary system consists of three primary phase wires. On the delta phasor diagram, primary phases are represented by points A, B, and C. In order to energize a transformer winding on a delta system, each end of the winding must be connected to a separate phase of the delta system. For the most part, the easiest way to identify a delta system in the field is to look at how the transformer is connected to the primary system. Notice that the H1 bushing on the left is connected through various protective devices to one of the primary phases. The H2 bushing on the right is connected in a similar manner to another phase. Provided that the primary winding of the transformer is rated for the phase-to-phase voltage of this primary delta system, it will function properly. On the phasor diagram for a Y system, points A, B, and C represent connections to each of the phase wires. Point N represents the grounded neutral. Each primary winding in this example is energized by connections between the energized phase and the system neutral. In the field, a transformer connected to a Y system looks like this. In this example, the H1 bushing on the transformer is connected to an individual phase wire. The case ground on the side of the transformer is connected to the grounded system neutral. Provided that the primary winding of this transformer is rated for the phase to neutral voltage of this Y primary system, the transformer should function properly. Here is an example of two bushing transformers connected to a Y primary system. In this example, the transformer is rated for the phase to neutral voltage of the Y system. The H1 bushing of the unit is connected through protective devices to a primary phase wire. The H2 bushing is connected to the grounded system neutral.